Okay, hi. So welcome to this will be the last lecture of the semester and of the year if you took Psych 607 as well. This one, I don't think a lot of stuff will be covered on the exam. I don't think any questions on multi-level modeling will be covered, but I think it helps to kind of solidify everything to present this. And then a lot of people think multi-level modeling is kind of the future of data analysis in the social sciences. So people like Richard McElreath think it's really important. And in a lot of ways, a lot of our data is kind of set up for multi-level structure. So I wanted to talk to at least present this information, and hopefully you'll find it useful, and then you'll be able to run these models. I think multi-level modeling could be a course in and of itself. So a lot of places it is. Unfortunately, our department doesn't currently offer a course just on that, but this is a good start. It's a brief introduction to multi-level modeling. It's based on Gelman and Hill's book, so data analysis using regression and multi-level hierarchical models. The book actually came out in 2007, but it's been kind of a classic since then. So Andrew Gelman, if you haven't heard of him, he's one of the most well-known statisticians in the world. I think he's still at Columbia. So he was one author. He's particularly well-known to us in psychology because he's one of the biggest critics of unreliable social cognition research. So he was one of the people, posting on his blog that, well, these results they look kind of fishy or don't look reliable. And so he would be really critical of stuff that didn't pass the smell test and seemed like it wouldn't replicate. And then Jennifer Hill is also a well-known statistician. She's now at NYU. So I think both her and Andrew Gelman were both students of Donald Rubin, who's also a very famous statistician as well. So I really regard them highly, and they really know quite a lot, and I'm glad they're around to teach us these interesting new things. Both were PhD students of Donald Rubin. So possibility for this summer. So one thing you could consider doing this summer is buy the Gelman and Hill book, or maybe ask your advisor to get it if you're brave enough and your advisor has funds or whatever. Read it all the way through until you understand it and do the exercise. So you might kind of think, what? You want me to teach myself? But yeah, I do think you should teach yourself, because ultimately you teach yourself everything, I think. And if you can do that, then you'll, if you do take a multi-level modeling course, it'll make it a lot easier. And sometimes you can learn things this way without really taking the courses. So I think that's definitely possible. If you don't want to read it all the way through, you could just read the parts that you think are most relevant to you. Some of the stuff may be on bugs and stuff for the Bayesian analysis isn't really necessary nowadays, because I think you can use BRMS, which interfaces with STAN, a lot easier. And of course, you can use it in your own research. So you can start, if you have data that's similar to the examples we'll be talking about today, you could start using it to analyze your own data, and then you'll be using a cutting-edge technique that I think is pretty well regarded, and it should be well regarded by reviewers who ultimately will review your great papers that you'll submit and hopefully publish. So the book focuses on using R, which we've focused a lot on, and bugs. So bugs is like an older Bayesian sampler. So Andrew Gelman has since developed STAN, so a better Bayesian Markov chain Monte Carlo sampler than bugs. So what is multi-level regression? So a lot of today, I'm pretty much just going to focus on examples because we don't have a whole lot of time for background. At the end, I do have some slides appended that you'll get. And so if you want to read through those kind of just rehash some of the information presented in the early chapters of their book. Consider a study with data from students in many schools, predicting in each school the students' grades on a test, given each student's pre-test score, say X, and then other info as well. So we could fit a separate regression within each school. So just in each school, say we predict grades based on pretest grades. And then additionally, the parameters for each school could be modeled as well. So if schools differ on characteristics like their average socioeconomic status, whether it's a public or private school, what state it's located in, what zip code it's located in, other variables for the school, funding it receives from the state, things like that. So the student level regression and the school level regression are the two levels of a multi-level model. So like we could predict students' grades just based on what school they're from the average socioeconomic status. We could also, within the school level, predict their grades given each student's pretest scores. So we have two levels. One's like the student level with student level variables of their pretest scores. The other is school level, so each school has a lot of students. And then those schools each have their own variables that could be used as predictors. So these are two separate regressions, and they're part of a multi-level model. So we have two levels, student level and school level. We could have additional levels as well. I think today we'll mainly be focusing on two different levels. Okay, so the model, which is multi-level in nature, could be expressed as a student level classical regression. So we could express the model as one where the coefficients vary by school as well. Okay, so instead of y equals b naught plus b1 times x plus error, so we haven't been using that a whole lot, but assume that there's some error variance. We would have y equals b naught for each j school plus b1 for each j school. So we would have separate coefficients based on each j school. So each school would get one slope and one intercept. Okay, so we could also have a model with variance components for student level and school level variations. How much variance is there in the student level of pretest scores? How much variance is there, say, in the school level of something like socioeconomic status amongst the schools? We could also have a regression with many predictors, including an indicator variable for each school in the data. So imagine, if there's 10 schools, you would need 10 minus 1 or 9 dummy codes. Of course, if there's hundreds of schools, you would need hundreds of dummy codes, which would get quite unwieldy. So instead of those kind of separate regressions, what if we consider a multi-level model to be a regression or a general linear model in which the regression coefficients, so our parameters, are given a probability model. So like the probability that these are the best coefficients or the expected value for the coefficients. And then the model also models variation in these coefficients. Okay, so variation across the different levels of like school or something. So this second level model has parameters, so coefficients of its own, the hyperparameters, which are also estimated from the data. Okay, so the two key parts of a multi-level model are varying coefficients and a probability model for those varying coefficients. So this could include group level indicators like socioeconomic status for schools. So you might have a model that models the variance in socioeconomic status across schools, and then within that we have a lower level model that models the variance in pretest scores across students. So when we learned about categorical predictors, we learned that classical regression can sometimes accommodate varying coefficients by using indicators like dummy codes, effects codes, contrast codes, things like that. So from this we learned that having a lot of categorical variables becomes unwieldy because we need k-1 predictors. So the key feature that distinguishes multi-level from classical regression is that we model variation between groups instead of just using indicators. So normally we just use an indicator and say, okay, well this is an indicator for each school. How do we adjust the coefficients for each school? Here we model that variation. We say, okay, well there's going to be variability at the school level. Let's, instead of just using indicators, let's model that variation. So this allows us to have much fewer predictors because instead we just model how effects vary across different categorical variables. Okay, so for example, how does the effect of pretest score vary across different schools? Okay, so multi-level models, you might also hear them called hierarchical models, also called hierarchical linear modeling, or HLM. So one reason for this is the structure of the data is often hierarchical. So students clustered within schools, say patients clustered within hospitals, or repeated measures, which is the last example that I added. So here it might be, say, trials or test sessions within subjects. Okay, so another reason is the structure of the model itself. So parameters of the within school regressions are at the bottom of the hierarchy, and they're controlled by the hyperparameters, the school level of the upper model. Okay, so models with 3 or more levels could also be handled, but we won't really get into those today. So say students within schools, within districts could also be modeled. So it can also be called mixed effects modeling. So mixed effects because we have fixed and random effects. So the coefficients that are being modeled as a distribution are called random effects. And then fixed effects are either parameters that don't vary, so like using the same regression line for all schools, or they're parameters that vary but they're not modeled as a distribution. So they're just modeled as single variables. So for example, the student level coefficient predicting scores from pretest is modeled as fixed across schools. Okay, and then there's just school level variability. The effect of school is random because it's drawn from a distribution. So Gelman and Hill and others I've seen don't like these terms because fixed effects are really just special cases of random effects, and the terms can be confusing for other reasons. So because fixed effects are special cases of random effects, multi-level modeling could also just be called random effects modeling. So it obviously has a lot of aliases, the different terms for multi-level modeling. But what we mean by random effects is that instead of getting fixed point estimates, we randomly draw higher level parameters from the probability distribution that those parameters are used to estimate. So by modeling many parameters as truly random effects, we can include many more predictors in the model. So because these parameters are distributions rather than single fixed points that would be represented by indicator variables, we account for their unreliability by modeling them as distributions rather than just point estimates. So we model, for example, how much variability there is in the effect of pretest scores on post-test scores across different schools. Okay, so that effect might vary across our different schools. So these are a couple of examples I'll just mention briefly, but these are from the book. So one is radon measurement. So radon is known to cause lung cancer. The EPA measured radon in 80,000 homes throughout the country. The data were structured hierarchically as homes within counties. So we have individual homes with their some home level variables, and then we also have counties that have many homes within them, and they might have different variables per county as well. So an important home level predictor is dichotomous, so it's this floor. So this is just a dichotomous variable of whether the first floor of the house was a basement or not. So radon enters via the ground. Of course, you know, in most of Texas that I know of, we can't have basements very well because we have a low, or I guess a high water table. This was really disappointing to me as a kid. I remember visiting some friends' relatives up in like Iowa, and they had a basement, and I was like, whoa, they have this amazing basement. Why can't we have one? But unfortunately we can't. And as you can see from our psychology building, and if you're aware of how it gets flooded all the time, I think that's because they keep trying to build it in the basement. So anyhow, so there's an important home level predictor is floor. So every home has that variable. Just say 1 if it has a basement versus 0 if it doesn't. And then there's also a county level predictor that's a measure of soil uranium. So say average soil uranium across the county, and uranium is a precursor for radon. So obviously there should be higher risk of radon in soils with, or soil counties with, that have soils with higher uranium levels. So the model predicted log radon measurement from floor and then county level uranium. Okay, so this example is covered in chapter 12 of the Gelman and Hill textbook. Another example from their book, the outcome variable was whether the voter preferred Bush or Dukakis in the 1988 election. So this is probably before quite a few of you were born. So in this example, there were 85 predictors. So things like gender, race, education, state, region, Republican share of the vote in the previous election, and then several interaction terms, age by education. So 85 predictors, quite a lot. In classical regression, fitting this many predictors would lead to unreliable estimates. But with a multi-level model, the coefficients are fit to their own probability distributions, and this makes it possible to include all predictors in the model. So the idea is they come from these distributions of variables rather than just being single point estimates. And so since we're modeling distributions, it makes it a lot easier to account for more variables. So this example is discussed in chapter 14 of the text, and I'm pretty sure the data is still available on the book's website. So if you want, you could look more into these examples and pull the data yourself and then analyze it yourself if you want to. So I've appended some slides at the end on motivations for multi-level models. This is basically kind of coming from their textbook, but here's a summary of the advantages that they note. We can learn about the treatment effects that vary by group, session, or condition. We can leverage all the data to estimate effects for small groups. So the idea is that we leverage all the data and then we kind of weight that data more, which allows us to make better inferences for small groups with fewer data points. We can have better prediction, particularly for subjects from new groups. These are readily set up for hierarchically structured data. So if that's the way your data is structured, then a multi-level model is probably right for you. You have better inference of regression parameters, so more reliable inference. You can include predictors at 2 different levels, so we'll show at least one example where we do that. And then you can accurately account for uncertainty in prediction estimation, because uncertainty is built into the probability distributions of the parameters. Okay, so as mentioned earlier, the book focuses on using R and bugs for multi-level modeling. It also has valuable scripts to generate plots. So I've actually, I think, adapted some of those scripts in the examples that I'll show today. The R package LME4 is probably the most common. You can find many examples online. It's been around probably for 15, maybe close to 20 years now. NLME is a similar package. I've mentioned this throughout the course, but I highly recommend a newer package called BRMS, which uses STAN to get Bayesian parameter estimates. This is often better for complex models that sometimes can't converge to a solution using LME4 or standard methods. So in the book, Appendix C gives instructions for on how to get started using R and bugs. It also provides some examples of multi-level models that can be fit using Stata, SAS, and SPSS. So if you're really committed to SPSS, well, first I hope you'll eventually break that habit and move to R. But you can still do some multi-level models in SPSS. So SPSS's mixed function can fit some types of multi-level models. Gelman and Hill, even in 2007, noted that they preferred R because of its flexibility. An additional reason to prefer transitioning to R for these more complex analyses is that you can't fit multi-level logistic, multi-level Poisson, and non-nested linear regressions using SPSS, or at least Gelman and Hill did not know how at the time of their book. So today we will be doing a multi-level logistic example at the end. Okay, so let's start off with our first example. So we're going to do a total of 3 examples, and then that'll basically be it for this lecture. So open up the multilevel modeling.r script in RStudio. Set your working directory in line 1. Okay, so if if yours is set somewhere different, you might want to copy it from a previous script that you've changed it in. Then run lines 1 through 9 to set the working directory and load the packages we'll use. I realized for lines 8 and 9 I could have just put library tidyverse, and both of these packages are in tidyverse. So if it says package not found, then you need to install that package by typing install.package and then the name of the package in quotes. So I'm not sure, some of you might not have installed LME4 yet, so you might need to type install.packages and then in quotes LME4 and then run line 7. So this is based on an online example where standardized test score is predicted based on the amount of time each student studied. So I think this was standardized learning time. So each student reported how much they studied, and then the average school size. Okay, so these are subject level and school level variables, and students come from several different schools. Okay, so standardized learning time is a subject level variable. Each subject varied in the learning time they reported, and then average school size is a school level variable. So all students from, say, one school are going to have the same value for the school size variable. Okay, so run lines 19 and 20 to load the data. You'll see up here in the script I give a link to where I got this example from. I didn't do this example recently, so hopefully the link still works. I think I made it about a year or 2 ago. Okay, so we're going to load the data. So that the data is actually in a CSV file in your Psych 671 RStats folder. Okay, and then here are the data right here. Okay, we see our norm exam score. Yeah, that's probably, whether it's maybe all boys or all girls school. School average. Some of these I'm not sure exactly what they are. But then standardized learning time is what we're going to use. And then I think we'll just use the school level indicator variable. Okay, and then average school size is right here. So you can see this is all for the same school. So school number denoted as 1. So these schools, if you type view data 3, you can view the whole data set in a new R window, and you would see that there's probably other schools than just 1. So this is the average school size. So it's all the same because we're all within the same school right here, but then we're going to have different standardized learning times and then different dependent variables for each student within school 1. Okay. So first we're just going to start with a null model with just the intercept for school included. So this intercept will just be the average exam score for each school. Okay, so this is kind of a pretty boring model, but we're kind of starting slow so you can see where the syntax is coming from. So run lines 24 and 25 to run the model and then generate the summary. Okay, so what we're doing here is we're saying LMER is the basic linear mixed effects regression command. So we're predicting norm exam just from the intercept. So these are our fixed effects right here. And then in parentheses, we put our random effects. So this says run it with just the intercept and then 1 intercept for each school. So 1 given school. Okay. So LMER doesn't give p-values, but it does give t-values. Okay, so Gelman and Hill compute confidence intervals for each coefficient by just multiplying the standard error by 2. Okay, so usually this is kind of approximates a 95% confidence interval. It kind of varies based on the actual critical t-value, whether it's like a little bit above 2 or a little bit below 2. But they use 2, and that's a pretty good heuristic. If you want to use that method, I think I've used it before actually in a paper and just cited Gelman and Hill in creating confidence intervals based on the standard error times 2. So there's one method and a book to cite kind of supporting that. So the standard error times 2 is 1/2 of the confidence interval. So for the full confidence interval, we would take the estimate and then add or subtract the standard error times 2. Okay, so fixed effects gives us estimates for the intercept only in this case, since we did not include predictors in the model. So there's our fixed effects. So we can see that the estimate is negative 0.01 and the standard error is 0.054. So a confidence interval would go from about negative 0.121 to 0.095. This obviously includes 0. So it's not surprising here, since scores are standardized and the mean is 0. It's no surprise that the intercept is not different from 0, because we expect that given the data. Okay, so random effects indicates the variability in the intercept, so the average test score across schools. So if we look at random effects right here, okay, so we can see that the standard deviation is 0.4142, which does suggest that some schools have, say, lower or higher scores on average than others. So their intercept differs from other schools. So this is a key part of what multi-level models model. They model this variability across schools, groups, subjects, trials, hospitals, etc. Okay, so here it's variability in the intercepts, so say the average standardized score across our school. So there is some variability. Okay, so however, we usually just kind of know that we're modeling this variability, and then most of the time we're more interested in the fixed effects. Okay, so now run line 26. So this is also potentially of interest. So this gives us the random intercepts for each school, or here their average test scores. Okay, so for like school 1, this is their intercept, and then all the way down to these different schools. So note that they're in scientific notation. So e to the negative 1, negative 0.1 means that we move the number 1 decimal place to the left, so that the first number would be 0.469. Okay, so this school has an average standardized test score of 0.469. So remember, these are standardized, so 0 is the overall mean. So this school scores slightly higher than average overall. Okay, the schools with negative values, so these some of these with negative values down here, that indicates that they score lower than average overall. Okay, so now let's make this model a little bit more interesting, and let's add standardized learning time as a student level predictor to see if study time had a positive relationship with test performance. Okay, we'd kind of hope that if you study more, then it's going to help you on the exam. So run lines 29 and 30. So this model has a random intercept for school. So now we've added this predictor, this fixed effect, since it's not in the parentheses for our random effects over here. We've added this right here. Okay, and then we have just one intercept given each school. Okay, so this has a random intercept for school, but it doesn't have a random slope for school, which is, I think, what we'll do next. Okay, so it's modeled as a random effect. So it accounts for different average scores across the different schools. Okay, so here is our output. So random effects are specified by parentheses, and then like I was saying, the one given school means just multiply the intercept for school by 1. Okay, so there's our fixed effect right there. So we can see that the fixed effect of standardized learning time is quite large. The estimate is 0.563 and the standard error is only 0.012. So this confidence interval would certainly not include 0. Okay, so say half of our confidence interval is 2 times this, or 0.024. You subtract that from 0.563. That's gonna be about 0.54. So certainly different from 0. Okay, the large t value is another indicator that this is a very large effect. So now let's run line 31. The simple intercept for each school varies, but the slope is fixed at the overall fixed effect estimate. Okay, so these are the coefficients for each school. So the intercept is allowed to vary for each school. We model that variation because it's a random effect. But the slope for each school is the same as the fixed effect over here. Okay, so that doesn't change. That's kept constant across schools, or it's modeled as constant across schools. If we wanted to model it differently, then we would model random effects for standardized learning time within school as well. Okay, so we'll do that in a minute. So now run lines 33 through 38. This uses dplyr and ggplot to plot the slope for each school. Okay, so we can see there it is. So the slope is constant across schools, but the intercept varies. Okay, so a standard regression would not account for this intercept variance. Okay, so how did we get this exactly? So we used the fitted function, which is just given by, fitted is automatically given by any linear model command or basic regression commands. So the object that we estimated with the model allows us to apply the fitted function to it. So we use that fitted function and then mutate to get predicted scores based on standardized learning time. So these give us predicted scores from the model using the fitted function, and then we tell ggplot to use the x variable standardized learning time. Okay, and then y equals from data 3. So this is the pipe indicating that we're still calling data 3. Okay, and then the y-axis are the predicted scores, and then group and color denote that we want separate lines for school. Okay. So now let's run a different model. So run lines 41 and 42. This model will include both random slopes and random intercepts for school. So the main difference is that now we still have the fixed effect of standardized learning time. Now we're going to model standardized learning time given each school or within each school. Okay, so students within each school varied on how much time they studied, and so we're going to first model that within each school, and then we're modeling it overall. Okay, and so we can look at the results there. So the fixed effect didn't change much from the random intercepts only model. So here it's 0.557, there it was 0.563, so really not much of a difference at all. Okay, so now run line 43 to show the coefficients for school. Okay, so now both the intercept and the slopes vary by school. So for school 1, this is its intercept and its slope for predicting standard learning time. So we basically have all of these regression coefficients for each school, and then we have one coefficient that's kind of the average of all of these, or really that's taken as estimated separately and then simultaneously with these individual models. So the fixed effect is a combination of these random effects as well as the overall effects with school ignored. So specifically, if you want to know kind of what's under the hood, you can look in the Gelman and Hill textbook. So page 258 actually gives the equation by which we get the fixed effects from the combination of accounting for the random effects as well. So equation 12.4. So we can plot these random effects by running lines 45 and 50. Okay, so basically the same syntax we used to create a ggplot, but now with a different fitted model. So now you can see that both the slope and the intercept vary across our schools rather than just the intercept. So our lines, have subtly different slopes. Okay, so this is accounting for the effect of learning time varying across schools, and we model this variability. Okay, so this plotting something like this, could be a reasonable final plot if you want to show the effects across all your schools, and then you also kind of can gauge the fixed effect as really the average of all of these effects across our schools. Okay, so I have seen plots like this done before. So the random effects output quantifies the standard deviation for the slope across schools, so 0.12, and the intercept 0.30. Okay, or that's about how much they vary, or what one standard deviation of variance is. So now go ahead and run lines 53 and 54. So this model is the same as the one we just did, except now we have added a school level variable, school average, which is the average enrollment for each school. Okay, so maybe schools that are larger in size, get more funding or something, and so that helps them, teach the exam better or something like that. Okay, so there's school average. Okay, so the fixed effect for school appears to be non-zero. Okay, so a confidence interval would be 0.29 plus 2 times the standard error, so 0.107. Okay, so this wouldn't include 0. Okay, so maybe not quite as big of an effect as learning time, but there still does appear to be an effect of the average school size in predicting standardized test performance. Okay, so it's also positive, so we can infer that scores are higher at larger schools. So the estimate is positive, in other words. So now run lines 55 to show the coefficients. So we now account for the fixed effect of school average. Okay, so these are the actual models for each school. So there's a fixed effect for school average, and then there are random effects for intercept and standardized learning time. So comparison with the coefficients from the previous model shows some minor differences in the random slopes and intercepts. So like for school 1, the intercept is 0.3155. Here it's 0.3637. Okay, the slope is slightly different as well, but for the most part there aren't a whole lot of huge differences. So this one was a little bit negative, now it's still around 0. Okay, the slope is about the same. Okay, so here when we've accounted for average school size, it changed these effects a little bit because these are all being estimated simultaneously, but it really didn't change them a whole lot, which is pretty common. Okay, so now run lines 57 to 62 to plot the random slopes for this last model. So these from the latest model look very similar to the ones from the previous model, but now in this model we've accounted for school average, or average school size. It's a significant predictor, so we probably would want to account for that. So run lines 64 through 69 to see the scatter plot between average school size and the model's predicted scores. Okay, so there it is right there. It does look like a positive effect of school size. So as school size gets larger, you get higher standardized test scores. Okay, it could be for multiple reasons. I think it's kind of well documented. Say small schools like in rural areas generally don't score as high. Okay, so the data appear to be in vertical bands, if you'll notice along the x-axis. So this is because each one of those is a school with the dots representing students within each school. Okay, so these kind of bands are all from one school, and then these dots are like different predicted scores based on learning time or study time between students within each school. So so you could kind of draw distributions within each of these bands, and they're probably approximately normally distributed. You can see fewer points like at the tails than in the middle. So finally, run lines 73 through 74. So this now includes an interaction between standardized learning time and school average. Okay, so now there's our interaction. So there appears to be at least a modest interaction effect estimates. Okay, so if we take the standard error times 2 and then plus or minus the fixed effect, looks like that still doesn't include 0. So you can run line 75 if you want to see the coefficients. So BRMS is a Bayesian and newer alternative to LME4. Since I didn't have time, I actually do plot these when in the one I just made that we'll talk about in a minute. But I didn't have time to plot the interaction effect in this example. I just ran the same model with BRMS and then used its marginal effects command to plot the interaction. Okay, so if you would like to run the model with BRMS, you can run it in lines 78 through 80. It probably will take a few minutes at least for this one. The fixed effects are called population effects, population level effects. So that's what you'd want to look at for fixed effects from a BRMS model. So this is the output from LME4. If we look at these coefficients, these fixed effects coefficients between the same model estimated with BRMS versus LME4, we can see that the estimates are about the same. So negative 0.01, 0.56, 0.37, and 0.16. So yeah, they're actually exactly the same, rounded to 2 decimal places. And then of course BRMS gives the error, and then it gives our lower 95% and upper 95% credible interval bounds. These effective sample size, like higher is better. So this means that like the effective sample size for estimating this effect was 2,038 participants. That's great. R hat is better as it approaches 1. So if you have R hat that are much higher than these and a low effective sample size, then it might indicate that it was kind of hard to estimate that model. You could also look at the Markov chain Monte Carlo chains in BRMS and see if those are off, if you have kind of bad diagnostics like this. So you can run line 81 to see the marginal effects plots. So here's our effect of learning time. Okay, and then here's our effect of school average. And then for the interaction, it looks like the effect of learning time increases as school size increases. Okay, so there's the largest school in red, largest school size in red, so 1 standard deviation above the mean, and then the green, and then the blue is this little shallowest slope. Okay, so strongest effect within schools that have a larger school size. Okay, so the next example, this one we'll just do pretty quick. So lines 84 through 111 use the sleep study data set. This is data sets actually built into LME4. So if you have the package loaded, you can load the data set. So here reaction time is measured over a period of days as subjects underwent sleep deprivation. So I'm not sure if this was total sleep deprivation or what. I think days is like a week, so I can't imagine staying up that long, but maybe they were paid a lot as subjects or something. I don't know, hopefully. So you can run lines 87 through 92 to fit the model. So here we're just using a model predicting reaction time from days, and then we also have days estimated as a random effect for each subject. Okay, so the effective days within each subject. So we model for, say, subject 1, what is the effective day on reaction time for them? That's being modeled by these random effects. And then the overall fixed effect is given by just days over here. Okay, so there's our fixed effects of days. Okay, so the estimate is 10.47. The error is about 1.5. So say 10 minus 3 is about 10.747 minus about 3 is still 7, well above 0. T-value of 6.771. So there's clearly an effect. So reaction time increases. In other words, people are slower as the number of days of sleep deprivation increases. So of course you would expect that, as you don't get any sleep, you're just, you're slower to move all around, especially in a reaction time study or something like that. So you can run lines 101, and maybe below that to plot the random slopes for each subject. So these are them right here. So interestingly, say if you look at these flatliners down here, you can see that sleep deprivation didn't affect reaction time much at all in a couple of subjects. So I don't know if a few robots slipped in or what, but I mean, these are days, going on maybe 9 days or 8 days, and there's no effect of reaction time. That's pretty interesting. But for most subjects, there are kind of these slopes right here. And so you can see that as days of sleep deprivation increases, you get longer average reaction times. So run lines 109 through 111 to plot the actual reaction time. So that's these over here. Okay, so these are obviously not as straight as the linear slopes. But you can see that they kind of mirror it. Okay, so like the subject represented by the blue line up here. Okay, the nice thing is we use the same color scheme, so the lines are going to be the same color. So their actual data look fairly similar to the slope plotted here. Okay, this is obviously a much simpler, only one parameter, or a zero bend curve, whereas here these are just the actual data, so they can take on any shape. So now for the last example, we'll do an example where we predict whether participants will accept or reject a mixed gamble on each of 256 trials. So this is one where instead of looking like within each subject, we're still going to have subject level effects. But here, this is going to be like at a trial level. So we can look at trial level effects here and model them. Okay, so open up the multi-level model _trial_level.R script. So this is one that I just created because I wanted to add in this example. It both is an example of like a trial level variable. So if you, this is very, very common in cognitive psychology, but a lot of times we collect data where there's multiple trials. People do something like over and over again. And then that's also common in social cognition, sometimes clinical work. You'll have people do stuff like that. So this is pretty common to a lot of data types. You have repeated measurements of the same subject. A lot of times we might just average across all trials and get average variables and then look at those at the subject level. But here we can also do trial level of analyses by analyzing it as a multi-level model. So that's what we're going to do here. So you probably don't need to run lines 2 through 5. So up here, since the working directory is probably still set for you if you did those first examples in the previous slide. But if you didn't for some reason, run lines 2 through 5 after changing the path to wherever your Psych 671 RStats folder is in line 2. And then run lines 7 to 8 to load the packages. So LME4, and these are probably already installed. And then Tidyverse. So I think in the last one we didn't load Tidyverse, we just loaded some sub packages. We are going to be using a tidyr package, which I think is part of Tidyverse, so I recommend just loading that. Okay, so you can, this gives, then when you run lines 10 and 11, this presents the data right here. Okay, if you want to look at the data more up close, you can, in the command line, type view data mg, so what I called this data file. Or if you want, you can open the data file in Excel and just like scroll down and see. So there are about 256 rows of data for each subject, and then the data is concatenated by subject. So in the data file, the first 256 rows are for subject 1, and then the next 256 rows, so lines 257 through 512, are going to be for subject 2, and then after that, subject 3, and so on. Okay, so they're going to be concatenated. So here are the different variables. We'll talk more about the ones we're going to use in just a minute. So what people did and the participants did on each trial is they decided whether they wanted to accept or reject a gamble. So this is reject down here. So that's our main dependent variable. We're going to code it as accept in a minute, just because I think I like working with positive associations better than negative associations. So there's reject. So you can see on each trial, if they rejected it, it's a 1. If they accepted it, it's a 0. Okay, but there is a 50% chance of gaining amount X and a 50% chance of losing amount Y. So this study's been done by other people. I probably should have found a reference, but I think it's often called the mixed gambles task. So you can see gain right here is the amount that they were told they could gain, a 50% chance of gaining $20, say, or a 50% chance of losing $6. Would you take that gamble? And so you can see the first line, they did not reject it, so they took that gamble because gain is so much bigger than loss. Here, let's look at row 3. So here they have 50% chance of gaining 10, but a 50% chance of losing 13. So would you accept that gamble? They rejected it. So 1 for reject. Okay, so gain and loss show the amount that they could gain or lose per trial. And then we combine these into a variable called expected value, or EV. This will be our main predictor that we're going to use. Expected value is computed from a normative economic standpoint as the probability for gaining times the amount that you would gain minus the probability for losing times the amount that you stand to lose. Okay, so here say 20 times 0.5 is 10, and then minus 6 times 0.5 is 3, so 10 minus 3 gives us an expected value of 7. Okay, here we have a negative expected value for 10 versus 13. That's a bad gamble. Okay, so that, like, I think I mentioned this in the lottery example in the logistic regression, but yeah, that the same way of computing expected value for a lottery or something, this is how you would compute it here. Okay, so reject is 1 if they rejected or 0 if they accepted. Since we think expected value is going to positively predict accepting the gamble, run lines 14 and 15 to create a new accept variable. So this will be our new dependent variable that we use. So I use this if-else statement again. So calling the data reject, the reject variable, using 2 equal signs because you have to for like a conditional statement like this. So if it equals 1, then that value now equals 0. So accept equals 0. Otherwise, if it equals 0, then it equals 1. So accept equals 1. Okay, so now run lines 17 through 18. So this runs a logistic regression predicting accept from expected value. Okay, so we also include random slopes and intercepts of expected value for each subject. So within each subject, we can model like their tendency to accept the gamble based on what the expected value was on each trial. So we're getting like a nice trial level analysis. And then we also get the fixed effect just across all subjects. So overall, like what's the likelihood of accepting given the expected value? So here are our results right here. So looking at the fixed effects, it looks like there's a very large effect of expected value. So no surprise really, people tend to accept gambles with higher expected value. So you can run line 19. This will show the random slopes and intercepts, predicting expected value for each subject. Okay, so I guess we didn't have all of the subject numbers exactly in order. But yeah, for subject 1, there's their intercept, there's their slope. For subject 3, there's their intercept, there's their slope. So for each subject, we get that. Okay, so these random slopes right here for expected value, that could be potentially used as like an individual level dependent variable. So like each subject's kind of slope for predicting accepting versus as a function of expected value. So higher values should indicate kind of steeper slopes. In other words, that expected value maybe had a stronger effect on whether they would accept or reject the gamble. So these random slopes for mixed effects models from trial level analyses like this, they've been used a lot in work. So one example is Otto et al.'s PNAS paper. But for example, some work has looked at model-based versus model-free types of decision making, and those metrics are given from a mixed effects regression similar to this, where you get coefficients, and then those coefficients are like the model-based index or the model-free index. Okay, but here we might use it as like an index of just, say, reward sensitivity or something like that. We could use it as like a subject level variable. Okay, so run lines 23 through 28 to plot the simple regression lines for each subject. Okay, so here they are. So the nice thing about this is we can see that this fitted function automatically appears to have plotted the slopes in terms of probabilities rather than log odds, which is great. So if they were log odds, it would be like simple slopes. One thing I didn't mention about the coefficients here is that, since this is a logistic regression, we might want to take the exponents of each coefficient to give us the odds ratios rather than just the logits or the log odds. Okay, so here, so in other words, these are all our individual slopes for each subject. So here, you could see that, up here, this is kind of weird. So this might indicate that these participants were like just kind of pressing buttons because they basically accepted every time. Here, these slopes are kind of around the middle. Maybe these participants were also behaving randomly. Maybe they were like alternating accept or reject, just kind of pressing buttons randomly and about the same time. But then what you would expect are these kind of, S-shaped curves where there is an effect of expected value in predicting accepting or rejecting. So this data is actually data that we just collected this semester. So, it's something we might look at if we're considering like excluding subjects for really not, participating in the task. We might think about looking at subjects like this who have basically no slope. So now we'll plot the fixed effects. So the fixed effect, first run lines 35 to pull the fixed effects coefficients from the model. Okay, so this fix F, you can apply that to these model objects, and then you tell it to give you the first coefficient. So that'll be the intercept. So we call that B naught, and then EV slope. We get that from the second fixed effect coefficient from the model. So now let's get the range of expected values to use as the range of the x-axis by running lines 38 through 43. All this did was it told R to find the minimum of the expected value from the data set, and then the maximum as well. And then our range is going to be, we're going to use the sequence command from the minimum value to the maximum value by intervals of 1 unit. So we could do by intervals of 0.5 if we want, but I think this is probably okay for creating the plot. So then run lines 46 through 49 to get the predicted values. So first in logits and then in probabilities. So here's our predicted values in logits. We just take the intercept and then plus the slope times the range. So this is actually vectorized notation. The range is going to be a range of variables, whereas our slope and intercept are just specific coefficients. But when we apply it to a range, it's going to give us a predicted range of predicted logits given each value of expected value in the range. And then we take those predicted log odds and we convert them to probabilities using the formula to convert from logits to probabilities that I mentioned in the logistic regression lecture. So now that we have those, run lines 52 to 53 to create a data frame with the predicted values. Okay, so I'm telling it to give me this new data frame. I'm going to call it plot.data as a data frame. Probability accept equals EV probs, and then EV equals EV range. So these are variables that we computed, or they're vectors that we computed on the previous rows, and now we're calling them prob accept and EV in the range. Or in our plot data frame. So now you can run lines 55 to 59 to plot the fixed effect slope. So this is the fixed effect average across all subjects. Okay, so here's the syntax right here. So you can see that I call plot data, which I created up here. Our aesthetics, x equals expected value right here. Y equals the probability of accepting. Okay, and then the rest is just kind of labels, and then I added this right here to center the title. Okay, the default is to left justify it, but I like it centered. Okay, so now we'll run a model examining whether sex interacts with expected value to predict accept. Okay, so first run line 63 to create sex variable as a categorical factor. Okay, so it was labeled gender in the original data set, but I think we were really kind of measuring sex. I don't think we asked people what gender they were. I think they just kind of wrote it down based on physical appearance. So we're gonna treat this variable as sex. Okay, and then we're gonna call it female and male. And the original gender was coded as 1 for female or 2 for male. So if it equals 1, then they're labeled female. If not, they're labeled male. Okay, so now we have that variable. And then run lines 67 through 68 to run the model. Okay, so there is the model right there. So note that we're testing the interaction term because we use this asterisk. So it's telling that. And then, so sex doesn't vary within subjects. So, it's one subject, then they retain their same sex for the whole study. So, but expected value does. So here we have one kind of group level predictor and then one subject level predictor. Okay, so they're either in the male versus female group, but then we can model the random effects of expected value within subject as well, while simultaneously estimating the interaction between expected value and this group level variable. Okay, and so we can see that the interaction is significant. So it looks like there's significant interaction here. I'm not sure why, but if you use, so one thing, we had to use GLMER and specify family as binomial because this is a logistic regression. I don't exactly know why LMER doesn't include p-values, and then we can see p-values are included with GLMER. I don't really know why, but maybe there's probably some reason, but I don't know why. So you could go try to find that information on the internet or something if you want. Okay, so it looks like there's a significant expected value by sex interaction. Okay, expected value is significant for the reference group. Okay, so that's right here. The reference group is females. Okay, because the f comes before m, so remember that it treats the variables. The first one alphabetically is going to be the reference group. This tells us that there is not an effect of sex when expected value equals 0. So that's probably not surprising. When the expected value is 0, then maybe males and females behave the same way. So now let's plot the fixed effect slope separately for males and females, and this might indicate kind of the locus of the interaction. So run lines 72 to 75 to extract the coefficient. So before we just had 2 coefficients, now we have an additional predictor for sex and then an interaction term as well. And then run lines 78 through 79 to get the predicted logits for females. Okay, so they are the reference group, so they are just given by the intercept plus the value for slope, for expected value slope. Okay, we're using the same range that we used before because expected value is the same range, so we computed that above. Then run lines 81 and 82 to get the same for males. So for males, their intercept is B0 plus the coefficient for sex, so the intercept difference for sex, and then plus the slope coefficient plus the intercept, the interaction term, which is the difference in slope between males versus females. So we got our slope right here multiplied by the range of the data. So run lines 85 and 86 to convert to probabilities. Okay, so we took these logits and converted them to probabilities just like we did in the previous model. And then now let's run lines 89 to 90 to put the predicted data into a data frame. Okay, so we're making a new data frame. The variable female is the female probs, male is the male probs, and then EV is our expected value range. So then run lines 92 to 93. This will put the data frame into long format. So this is wide format, but we need it collapsed into like a long format. So it puts it in long format that's required for ggplots. Okay, so this gather command comes from the tidyr package. So if it's not working for some reason, I think it's part of tidyverse, but go ahead and do install.packages and then tidyr in parentheses and load that library, but I think it should work. Okay, so gather takes multiple columns. So here we want male and female to be collapsed, and so it collapses them into key value pairs. Okay, so so key is the first command. We call the key group. Okay, and then we call the value probability. So that's these values that we're collapsing. And then we state what groups we want to collapse across. So from female to male. And so now we have this new data frame. Now we have expected value. And then we have this group level variable. And then we have the estimated probability. Okay, and so if you looked further down, if you could type view plot data if you want, and then it would show you like the male predictions down here. So finally run lines 95 to 96 to plot the slope separately by group. Okay, so we can see our plot right here. So this is the slope for male, and then this is the slope for female. So we could tell by the coefficients that the slope is going to be steeper for male because it's the interaction is positive. Okay, but we can also see it in the plot. So color equals group is what tells ggplot to plot the separate slopes for group. So males appear to have a steeper slope from expected value predicting acceptance of the gamble. This could be interpreted as like a more strict cutoff for accepting gambles. You could also interpret it as maybe higher reward sensitivity in males. It kind of indicates that their probability of acceptance goes above 0.5 in a steeper way. Okay, so in other words, they might have kind of a threshold that they're more stringently applying on average than female participants. Okay, but that kind of plots the interaction. So you can also run the same model using BRMS. However, it'll likely take longer, probably about an hour. So mine's been running. Hopefully it's done. I'm about to check. Since there are so many data points and it's modeling an interaction. So here the difference is BRM. So let's go ahead and let me see if that's done. I'll try to pull that up. So here it is right here. Oh yeah, and so it's finished finally. I don't know how long it took. But we can see these are our estimates. Let's plot the marginal effects. Okay, so marginal effects for this. So there's our first plot for expected value. And then you press enter to get the next one. They're showing our differences just based on sex. So overall, males were more likely than females to accept gambles. To see if that's significant, we would probably need to just take out expected value overall from the model. Look at the lower order effect. And then here is the plot produced by BRMS. Okay, so we could see that here's the plot. I'll go ahead and copy it over here. See the, well, we don't have a place to copy it, so I won't. But there is the plot, and you can see that that plot is very similar to the one that we created in ggplot ourselves. Okay, so like I said, even Paul Berkner, who created the BRMS package, he says that, you know, this marginal effects command to plot the effects is actually one of the most useful, turned out to be one of the most useful things. So I don't have time to go into more detail, but I'll also be distributing this R file edit BRMS plot. So this was made by my current postdoc, Hillary Dawn. So she came up with that. What it is it basically allows you to extract the BRMS package. So you would call these, so you do the plot marginal effects command, and then you call that as an object. So save it as something like GG, and then you can plot, you can extract each plot separately. Okay, and then down here, like, so this would be the first plot that was shown, this would be the second plot, this would be the third plot, and then down here, you would take plot 1 and then you would modify it. So you could add different labels, you can add different themes and stuff like that. Okay, so I'll distribute that. If you do decide to use BRMS more and you actually want to use these plots in a paper, this would be really useful for like customizing them to get kind of the final nice, very nice looking plot. Okay, so yeah, so there's kind of the basic. You extract the plot objects, and then you get each plot separately, and then you can use that to call it again and modify it. Okay, so it allows for manually editing the BRMS plot. So to summarize, multi-level modeling is a topic for a course in and of itself, but hopefully now you have some of the basic ideas from regression extended to multi-level modeling. So these combined with fairly easy to learn software like R's LME4 package or BRMS should allow you to test multi-level models as they apply to your data. Okay, so it's important that you understand kind of the basic ideas behind this hierarchical setup, and also important to be sure to understand the syntax for LME4 if you choose to use it. So I have a number of additional slides that you'll get as well, so this might be useful. So this is a closer look at the syntax. So this was a syntax for that uranium example. I think I used to give that example a couple years ago. Okay, but you can see this discusses in more details the syntax and then different motivations for multi-level modeling. I think I summarized those. So there's more information if you're interested. So anyhow, that's it for today, and then that's it for the year. So that'll be the last lecture, and then hopefully, you know, you've learned a lot and learned a lot of useful things, not just, you know, learned a lot, but learned a lot of practical things. Okay, well, that is it.